welcome back to this Red Door Analytics online course, Survival Analysis and Introduction to Concepts, Methods and Software. In this section of the course, we'll be talking about rates. So an event rate describes a number of events by a measure of time and is always in the following format, where we have that the event rate is equal to the number of events divided by the time at risk. So if, for example, we're looking at a mortality rate, this is the number of deaths divided by the time at risk. An incidence rate is the number of new events divided by the time at risk. And this event rate could also be called a crude rate or an absolute rate. But note also that crude can also refer to unadjusted estimates from a model, not necessarily a non-parametric estimate as we have here. So, as you saw, a rate is the number of events divided by the time at risk. And we've covered time at risk previously in this course, but just to give you a quick reminder, this should be familiar to you, where we look at individuals here across this example of years since breast cancer diagnosis to death. And we said previously that the length of the lines represent the time at risk for each individual. And if we sum all of these times at risk for individuals across the whole population in the cohort in our study, then we would get the total person time at risk. And here this would be person years at risk because we have our time in years. And this is important when calculating rates. So we can present rates in different units depending on the time at risk unit. So, for example, you may have a mortality rate per 1,000 person years. You may have a hospitalized infections rate per 100,000 person months. So there's two aspects to think about when we talk about the unit here. We have the time unit. Are we looking at years? Are we looking at months? Are we looking at days? And then we also have the per unit here. So we can divide our rates by a value here. And we've got per 1,000 or per 100,000 here. So the way that you present an event rate may depend on the actual field that you're in. There may be a standard way of presenting rates. So let's look at an example of calculating a crude rate. And in this example, we are interested in estimating the rate of hospitalized infections at some specific hospital, where we select 50 individuals and we follow them for a total of 30 days. So we have our 50 individuals. If we follow them for 30 days, then we have a total of 1,500 person days. That's our total time at risk. And we observe 15 infections. Now, we know that a rate is just the number of events divided by the person time at risk. So we can calculate our crude rate as 15 events divided by our 1,500 person days to give us a rate of 0.01 infections per person day. Now, note here we have our unit as per person day because our time at risk was in person days. However, in reality, we don't actually follow every individual in the cohort for 30 days. So we may have something that looks like this, where we have days since hospitalization on our x-axis, and we have different individuals represented across the y-axis, where we see very clearly that actually we don't follow these individuals for the entire 30 days. These individuals may get an infection prior to 30 days. They may also be censored prior to the 30 days is over, meaning that our time at risk isn't really as we described it earlier. So in fact, what we see is that some individuals are censored at hospital discharge or death prior to those 30 days. And instead of following the 50 individuals for a total of 1,500 person days, as we calculated previously, we actually follow these individuals for 1,000 person days. So this means that we can calculate our crude rate as 15 events divided by 1,000 person days instead of 1,500, which gives us a rate of 0.015 infections per person day. Now, this is different to what we calculated previously when we used the incorrect follow-up time and we got a value of 0.01. So this should really illustrate to you that not accounting for the censoring and the time at risk correctly can bias our results. So it's really important to keep censoring and time at risk in mind. So let's go back to our example study where we were looking at breast cancer diagnoses in 686 patients in Germany, and we were looking at time to recurrence of breast cancer or death. So we can use the command sdrate in Stata to calculate this crude rate of recurrence or death. So what we would do, we would just use this command and we will get an estimate of the rate, which is the number of events of recurrence or death divided by the total person time at risk. So if we do that here, we can see that we have written just sdrate, and we would do this after we have sdset our data as described in the previous section of the course. So here we have our time since breast cancer diagnosis in years. And you can also see that here when we look at the output where we see analysis time is rec time divided by 365.24. We divided the days that we had in rec time divided by 365 in order to get our time in years. So what we get out from this output is D here, which represents the number of events. We saw this previously when we had the sdset output. This was 299 occurrences of reoccurrence of breast cancer or deaths in our patient population. We have Y here, which represents our person time at risk. So this is person years here. You can see that with this unit, it's quite difficult to interpret this. But what we do when we calculate the rate is that we calculate the number of events D divided by this person time at risk Y, and we get a rate of 0.14. So this is the rate of recurrence or death per person year. And we also have a lower and upper confidence interval for this rate. Now, what we can also do, because we saw previously that it was really difficult to look at those person time year, and we got quite a low rate, is we can use the per option to specify which unit the rate should be displayed in. So what I do here is I say sdrate again, but I use the option per 100. And the thing that changes in this output is the Y value here and the subsequent rates. So what we do actually is we divide the person time at risk by 100. And now we can see that we get 21.12. So that's person years per 100,000, per 100. And what we do to calculate the rate is then we divide the D divided by the Y, so the events divided by the person time, and we get a rate of 14.16. So now this is the same rate, but it's multiplied by 100. It means that we have a rate of recurrence or death combined, the outcome, of 14.157 per 100 person years. And we have our lower and upper confidence interval for that. So we said before that we were interested in our example data set to look at hormonal treatment. So one other thing that we may be interested in doing is calculating the crude mortality rates within each of these groups. So what we would do here, if we're interested in doing that, is use the sdrate command, specify our variable hormone, and then here we're going to use per 100 again. So we'll present the rate and the person years per 100 person years. And what we can see is that we get two lines in the output here, one that represents those individuals that didn't receive any hormonal therapy, and one that represents those that did receive hormonal therapy. And for each row, the rate is calculated as the number of events divided by the person time, again, so D divided by Y. And we end up with two rates here. We have a rate of 16.06 for those that didn't receive hormonal therapy, and a rate of 11.25 for those that did receive hormonal therapy. So we see that the rate of reoccurrence or death is higher in those that didn't receive hormonal therapy. And note again that the unit of this rate is per 100 person years. So we may be interested in calculating some sort of crude rate ratio of this. So we can take these two rates and calculate a rate ratio. So we would just do this by calculating the rate in the hormonal therapy divided by the rate in the non-treated group. And we could get a rate ratio here of 0.7. We may also be interested in calculating accrued rate difference, if that's of interest, where you just minus one value from the other. So that's all for rates for now. We'll be building on this topic as we go through the next sections of the course. Here's some further reading, and I will see you in the next section.